Hi, I'm Ashay. I'm an engineer by training and a storyteller by passion. I made this podcast to talk about data science, but no math, no equations, just intuitions behind data science. The episodes are not in any particular order, and you can just tune into any episode and listen to something related to data science. Let's get started. In this episode, I want to talk about the intuition behind the intercept of linear regression. So, whenever you create a linear regression equation for a particular sample space, what you are trying to do is you're trying to create a correlation equation for the sample space that will hold true for any other sample space within the same population. So you're trying to basically understand, as I said in one of my other episodes, you're trying to understand the recipe of your data, and then that recipe should hold true for any other sample space within the population. That's what your goal is. You want to generalize the equation so that you can understand the behavior of the data in some other space that you are not working in, right? So but what happens is, while you are creating this equation, you want to you don't want to overfit your equation to a particular sample space that you are working in, because if you overfit, it is going to give you much more information of only the sample space that you are working in, and it won't give correct information about other sample spaces that you are interested in. And you also don't want to introduce heavy bias in your equation. In other words, you don't want to underfit the equation for that particular sample space, because then it is not going to give you information about the exact sample space that you're working in. So forget about the other sample spaces. The sample space that you're working in, you may not get correct information about that particular sample space. So what you need to do is you need to have a good trade-off between the underfitting and overfitting, or between the bias and variance for the linear regression equation, so that you can so that you can have a good estimation, a generalized estimation of population parameters, right? So let's understand the intercepts part. So let's assume that we have only two-dimensional data. By that, what I mean is there are two features of the data in the sample space. One feature is an independent feature, and another feature is a dependent feature. And by that, what I mean is, the dependent feature is some linear function of the independent feature. So if the dependent feature is y and if the independent feature is x, then usually what we have seen is the equation comes down to y is equal to mx plus c, or mx plus b. Sometimes we call it mx plus b. Or in other words, the equation is the dependent feature is a multiplication of a slope and the dependent feature value plus some constant, and that constant in this equation is called intercept. Now, why do we need intercept in this? So think about it in the terms where the intercept is needed to have an independence to the dependent variable. So I would like to think it this way. So basically, think about it like this: if the dependent variable is zero, then the independent sorry the if the independent variable is zero, the dependent variable has to have some value. Because it if it becomes zero as well, if the independent variable is zero and if the dependent variable becomes zero, because of that, that means you are introducing a bias to the dependent variable, and you are forcing it to become zero when the independent variable becomes zero. You're forcing y to be 0 when x becomes 0, and you don't want that. You want that dependent variable, the dependent feature y, to have some value when your independent feature is 0. Now think about it this in the Cartesian coordinate system. You have an x-axis, you have a y-axis, and the line for the data is that y is equal to mx plus c, or mx plus b. Now what happens for that particular line is the line is going to have some slope, let's say positive slope, and the line is going to intersect the y-axis when the x becomes 0, and the value of y-axis, value at the y-axis when the x is 0, is the intercept, right? If the and that's how the line then can move along y-axis up and down, keeping the slope same, giving much more freedom to you to fit the line to the data that you have in that coordinate system. Now think about if the intercept is 0, or for example if the line equation of the line is only y is equal to mx. In that situation, what will happen when x becomes 0, y will also become 0. That means the line will pass through origin, and you don't want the line to pass through origin, because then you are forcing the y to be 0. Then the only thing that you could change in this scenario is the slope of that line. So the line is actually kind of like it has a pivot at origin, and then it is just moving, um, not up and down, but it is basically just tilting along the origin. And then if the data, the actual data in that two-dimensional system is at some other is in some space where it has to uh, it can't pass through origin, then you are introducing bias to the data, introducing bias to the equation that you are trying to come up for estimation of population parameter, and then you don't want that. And that's why intercept is basically kind of like an independence of the dependent variable, because it is the value of dependent variable when the independent variable is 0. Thanks. Thanks for tuning in. I made this podcast to talk about intuitions behind data science, and we'll talk about some other idea in the next episode. There will be no math, no equations, just intuitions behind data science. See you soon.